Hello, my name is Chris Cordle. I go by Chris Co. I'm here to present how to do on-chain chess in Rust using Arbitrum Stylus. For those of you that aren't familiar, Stylus is a new parallel execution VM on Arbitrum chains. Basically, any WebAssembly programming language is supported. That includes C, C++, Rust. Other niche languages like AssemblyScript and Zig are also supported. It allows up to 70 times more computation per unit of gas and as much as 1,000 times more memory per transaction compared with the EVM. All the while, it remains fully composable with the EVM, so you're able to write Solidity smart contracts, and you're able to write Rust contracts and have them talk to each other as needed. So you can still plug into the broader Arbitrum ecosystem. You don't have to give anything up. You just choose which execution environment that you want for your smart contract. Some of the other benefits of using Stylus is that you get access to general purpose language tooling, such as like crates.io, which is a package registry that Rust provides. Many other languages also have package registries. Solidity does not, so you really just have to import based off of GitHub repos and whatnot. So you get access to that. You've also got access to different coding paradigms, different design paradigms. Solidity is a very opinionated language. It has a lot of warts. So if you want to explore more of a functional style, or you want to use kind of Rust paradigms, or different design paradigms, it's a powerful concept there. Additionally, like the point of additional programming languages is to allow us to onboard Web 2 devs more easily and gain access to all the libraries and tools like cryptography and gaming libraries that exist in the ecosystem for that other developers are out there creating, that we can tap into in smart contract development as well. So just I'm just going to briefly go over what some of the prereqs are if you want to develop on Stylus. You can look all this up on docs.arbitrum.io to review and go through a little more slowly than this 20-minute presentation. So a little hard to keep up, but I'm going to go through it pretty quick. But just as a high-level overview, you need Rust installed on your system. You're going to need to make sure you have Rust up, Rust C, and Cargo, the CLI tools that you can use when you're coding in Rust. Also, just as a suggestion, you can use whatever editor you want, but VS Code with the Rust Analyzer is a good go-to for beginners in Rust. To deploy and test your Stylus contract, you're going to need Docker. And if you look up under Run a local dev node on the Arbitrum Stylus docs, you should find a section that will explain how to install a local Arbitrum Nitro test node that will allow you to run a local node and deploy locally on your system. We also have a public testnet that is currently in L3 on top of Arbitrum Sepolia. Stylus is currently still in audits, but we're getting very, very close to presenting this to the Arbitrum DAO to get approval for mainnet. So we're very excited about that. But in the meantime, you can deploy on top of the testnet. And the RPC for the testnet is right there, stylustestnet.arbitrum.io/RPC. So in order to write a contract in Rust, you're going to probably take advantage. You don't have to. You can make your own SDK if you want. But we provide a Rust SDK that leverages the library called Alloy, which is part of the Foundry team. A lot of the devs from the Foundry team also wrote Alloy. And that provides Solidity API compatibility. It helps, convert between Rust primitives and Solidity primitives, and kind of does it in a very aesthetic way that enables you to quickly switch back and forth between them and declare your state variables in a Solidity API compatible way. Optionally, you can use, while you're coding, and I'll show you in a sec, you can use either Solidity style declarations, so you can literally write basically Solidity syntax as part of your smart contract to declare your variables. So that makes it easy if you're like porting over something like an existing Solidity contract. Makes it really easy to make sure everything's lined up and in the same slot that it would be, especially if you're doing something like a proxy upgrade. A nice thing that we did with the SDKs, we disabled reentrancies by default. Reentrancies have caused like a lot of hacks and exploits. So we just disable it by default. You have to write unsafe code in order to enable it. This is just kind of like a high-level overview of the syntax, just a like real simple example. So basically, you just declare a struct. This is a counter contract with just a single count variable. And the Stylus SDK provides a set of storage primitives that you use when you're declaring your state variables on your contract. And this one is a U256, so it's just a standard 256-bit integer. So it's just a struct with counter. The count field with a U256, we declare that entry point to let the that's a macro that just lets us know, lets the SDK know which struct is the highest level or the root level of your contract state. You can declare multiple structs, and you can reference those from this root state, but this is just a very simple example. And then just to like implement methods on that contract, you just declare this external macro, and then you write your implementation methods. Very simple. Here we got getters, setters, and an incrementer. We're just returning a result that either has an OK or error. For the get, it's just returning the count. It's just called self.count.get. We tried to make getters and setters pretty explicit because accessing state, reading state, writing to state is the most expensive type of operation you can do on chain. So we wanted to make it a little more intentional than maybe Solidity is, where you kind of can accidentally refer to state variables just as easily as local variables. So we kind of try to make certain things like that getting and setting explicit. But moving on to chess. So if you want to make chess on chain, what are some of the key challenges that you're going to find? Well, the board is 8 by 8, 64 spaces. There's 32 game pieces. It's a complex move space, and you have to like validate the moves to make sure that each move is legal based on the rules that each piece has. There's 6 different types of pieces. They all have different rules about where on the board they can go. Doing this in Solidity is very difficult. In fact, I couldn't find an example of a full 8 by 8 chessboard. I found a 6 by 6, but I couldn't find a full 8 by 8 Solidity implementation. It might exist, but it's very expensive to do on Solidity due to the gas limitations. And one of the benefits of Stylus is you get that additional computation that allows us to validate whether a move is legal or not every time a player makes a move. And we're able to do it with a reasonable amount of gas. So one approach that a lot of developers figured out a long time ago about chess, if you want to make an efficient computation, even with this, it's something called bit boards, but even with this, it's difficult to do in Solidity. But essentially, like, it keeps a, this is kind of a simple 3 by 3 example to just kind of give you a high level overview of what's going on under the hood to like make this computation more efficient rather than like iterating through a list of pieces and checking whether or not it can move through each individual possible move. Iterating through all that would be computation expensive. So this makes it easy where you can just do like simple XOR operations to like bitwise operations to see which piece moved and to see whether that move was legal or not. I'm not going to go too much into bitboard implementations on this example because I want to get to the Rust code, but it's something that you can look up another time. It's used in a lot of gaming, for even in gaming environments where the computation is a bit restrained, and that includes Onchain. So, but you can kind of see here, as a simple example, we've got a board, a 3 by 3 with a pawn and a knight. On the pawn, there's basically 9 bits that represent the pawns. where pawns exist on the board. And you would have, I guess you would have two pawn bit boards, one for black, one for white. And then you can validate, for example, on the lower right, you can see where there's an old board, there's a new board, and how do you track which one moved? You just XOR the old board with the new board, and you get the diff, which tells you that the knight moved from B1 to C3. Again, if you want to review this, there's lots of resources online, lots of great YouTube videos. It's a very cool technique to understand. The other alternative is you can just use a library, because somebody's probably already rewritten this in Rust by now. So Rust has a nice package registry called crates.io, and if you want to use a library, you just look for certain things. You gotta when you're looking through for a stylus implementation, you have to look for something that doesn't use the standard library usually, because it can be a little bulky for Onchain. It could be lots of megabytes or whatever. So you might want to just look for something that's usually made for a no standard library environment. Usually those are focused on like systems or embedded systems types of deployment, but they work for Onchain too. You want to make sure there's no async operations in that code, no randomization. Randomization doesn't really work on chain. We need to be very deterministic about how execution goes. And currently there's no float, but we're planning on implementing a version of float soon. So something to look out for. But the library that I used for this demo is called just Chess Engine. You can find that on crates.io. And I'm going to kind of walk through the code real quick. So just to kind of give an example of what this looks like, and maybe I need to increase the font size. Maybe that's too big. No, let's do that. Okay, that's reasonably good. Might want to close that altogether. Okay, so I'm going to kind of skip over some details because I got to move quickly. This is just dependencies, and I've set a few constants to declare, like track game state, whether you can continue. After a move, it will return a game status, and it'll be one of these 4 integers that tells you whether that move was legal. If it was legal, it's going to return continuing. Otherwise, it's going to return an illegal move. Otherwise, it's also going to detect whether stalemate or victory was reached. If somebody's got checkmate, the engine will catch that and will return victory and set the game state on chain correctly. 0 is white, 1 is black. I've got a couple of consts for the different piece types, a couple of bit masks that I use because I'm basically storing the game state in a single 256-bit integer. That is to say, like basically each piece has one color and a row and column that I need 3 bits for and 1 bit for the color. So if you've got 4 bits per piece and there's 64 pieces or 64 positions on the board, to track a board you need 64 positions times 4 bits. So that's kind of like how I'm storing this in the games object here. So I just got a simple counter, tracks the total games, whether or not there's a pending game, and just a simple mapping that takes an ID and returns a game info struct. And notice I'm using Solidity style syntax here. I'm using mapping with the arrow, fat arrow. So it's using this like sol storage macro. So I'm kind of writing a little bit of Solidity syntax. Again, that's optional. You don't have to. You can just write pure Rust if you want. But it's nice to know. And if you're familiar with Solidity, it makes it a little easier for the ABI compatibility. But yeah, game info object is just made up of player 1's address, player 2's address, the status, the turn color, whose turn it is, whether there was a victor or not, which color won, and then the board state object that I just mentioned. The methods are quite simple, just tracking total games here. And again, I'm importing this chess engine, so it's doing the bulk of the computation. I didn't have to figure all this out by myself. I'm just leveraging the Rust ecosystem to use this chess engine to build this game. So that's just a simple counter that gets the color of the current term. That gets the current player, whether it's player 1 or player 2, and returns their address. This is a meteor function here. This is a play move. To play a move, we need to pass in a game number, a from row, a from column, a to row, and a to column. And it's a 0 through 7 based, 0 based index to track the row and the column. So in a typical chess game, you might say A7 to B3 or whatever. This is just a 0 through 8 index. So just kind of walking through. We've only got a few minutes, so I'm kind of going to really go through quickly so I can kind of show you all live demo real quick. But yeah, it's checking to make sure that the current sender for the game is the current player, making sure that the game isn't over already, and then it makes sure that the move, it goes through and makes sure that the move was legal, and returns the state and updates the state if it was a legal move. If victory, it's going to go ahead and set the victor. It's going to set the game status, and it's going to return that victory status code. It's also going to do the same for stalemate. And otherwise, the legal moves are just going to return a legal move and not change state. I got a simple printer function that you'll see in a sec that just shows you how to print the game board to the console. So nice thing about Stylus is while you're developing locally, you got access to a local console output that you can just output locally while you're developing, and it's really helpful for debugging. These are a couple of other methods. Let me just kind of do a quick demo just so I get a chance to show the game state. Let me go ahead and pull up my console real quick. So I've already got this deployed, but I think it should just go through. I should go through quick. So what it's doing right now, it's trying to get the code size under 24 kilobytes. That's the max size. It goes through Cargo Stylus goes through a couple of optimizations. It just deployed locally to this address. So I can copy that. And then I've kind of got this in my history. So I'm just going to use some of these functions that I've already written. But I've got a brand new contract that I just deployed, so I'm going to create or join that. So I'm going to go here and paste that contract address in, and I'm using Foundry's cast CLI. So I'm just calling cast send. That private key is public, so don't worry about seeing that on there. That's a public testnet private key. And then I'm calling creator join. I'm letting cast know what the function is that I'm calling on the contract, and that's just going to create a contract. It's going to create a game locally, and if I call total games, it should say 1 now. Now that I've created the 1, and let's move quickly because I only got a couple minutes. Well, this should be, one sec. Yeah, you went 256. That's going to, let me call it. Hard to do this, hang on. Hard to do this with the mic in my hand. I'm used to doing this 2 hands. Call, okay. So we got the 1 game. We're gonna go ahead and call creator join again. I can play against myself if I want. And then I'm going to call, I want print game. Print game. Oh, come on now. One sec. Play move. Print game state. Sorry, one sec. One. Okay, that's Okay, call. And what that's going to do is print. Yeah, it's going to print the game state. So we've got a fresh board. And then to make a move, I'm just going to demo the move real quick. Just basically, like I've got a board here, 1 through 8, row 1 through 8, column A through H, which corresponds to 0 through 7, both on the column and the row. So if I go back here to play a move. Let's go back here. Play a move. Okay. And I'm just going to make a move on one of the pawns. I'm going to move the pawn from row 1, column 3 to row 3, column 3. And that should send, and then if I call print game state again and go back, it's moved the chess piece. So, and every time it's making that move, it's also like on the on the green and the red kind of shows, and the monitor's a little messed up on the colors, but it'll show which piece is in threat mode right now. It's able to calculate all the pieces that are currently threatened, and yeah, it's a very cool little demo. Just to kind of go back to the presentation real quick, if you guys want to look at this example, you just go to github.com/offchainlabs/styluschess. It's on our, if you can't find it, just look up Offchain Labs, GitHub, and look through our repos. You should be able to find it on there. Docs.arbitrum.io for more SDK resources. We also have a Telegram, Arbitrum Stylus devs channel. And if you need me, I'm on Twitter and Telegram at ChrisCrow512. Thank you very much.